So I have come. Let's see. Today's topic is that atoms and molecules, right? So we'll be learning today atoms and molecules. Let's go the topic then. Let's go with the topic. Okay, I'm starting. Okay, so now, so wait a minute. I just let me on the video. Okay, you can see me right. There's some lighting coming. That's why you see this side. This side is sunlight's coming. That's why. So I will wait. Still it's coming, right? Okay, you cannot see me this way. Now you can see me, right? That's a little bit of blurry. If I do this, so let me close it. Wait a minute, let me close it. Let me close it. Let me close it. Let me close it. Now it's better. Still, you can see me, right? Now it's better, right? Now it's better. Now it's better. Now it's better. Sorry for the noises. My nephew is crying like it crazy. So So I'm back now. Now let's start the topic. So here is chapter 3. So atoms and molecules, right? So ancient Indian. So here is ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher Maharishi Kanand, an Indian philosopher Maharishi Kanand postulated that if we go on dividing matter, padarth, we shall get. An Indian philosopher, an Indian philosopher Maharishi Kanand, an Indian philosopher Maharishi Kanand postulated that if we go on dividing matter, padarth, an Indian philosopher Maharishi Kanand postulated that if we go on dividing matter, if we go on dividing matter, padarth, we shall get smaller and smaller particles. We shall get smaller and smaller particles. Ultimately particles postulated that if we go on dividing matter padarth, we shall get smaller and smaller particles. Ultimately a stage will come when we shall come close. Okay. So the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pak Pakhuda, another Indian philosopher, Pakhuda Katyayama, another philosopher, Pakhuda Katyayama elaborated this doctrine and said that these particles normally exist in a combined form which gives us various forms of matter around the same area. Ancient Greek philosophers ancient Greek philosopher Democritus and Leucippus Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Particles obtained cannot be divided further. So Democritus called these individual particles atoms, meaning indivisible. All this was based on philosophical considerations and not much experimental work to validate these ideas could be done till the 18th century. So by the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Okay. So Anthony L. Lavoisier laid the foundation. Who laid the foundation? Anthony L. Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combinations. So law of chemical combination. The following two laws of chemical combination were established after much experimentation by Lavoisier and Joseph L. Proust. So law of conservation of mass. What is law of conservation of mass? So is there a change in mass when a chemical reaction takes place? Law of conservation of mass. Right. So law of conservation of mass here. भाई कौन आया लेवल Sorry for the trouble, guys. I'm back. पता है तो you can understand, right? So, law of conservation of mass. What is law of conservation of mass? So, is there a change in mass when chemical change? When chemical, I will change the color here. I will take here red. So law of conservation mass. What is law of conservation mass? So law of conservation mass is there a change in mass when a chemical change? So chemical reaction takes place. Yes, shit. Yes, good. Take some of the following sets X and Y of chemicals. So X and Y. So one copper sulfate, second is sodium carbonates. Two barium chloride and sodium sulfate. Three lead nitrate, sodium chloride. So prepare separately a 5% solution of any one pair of substances listed under X and Y. Listed under X and Y, each in 10 ml in water. Take a little amount. Prepare a separate a 5% solution of any one pair of substances. Prepare separately a 5% solution of any one pair of substances listed under X and Y, each in 10 ml in water. Listed under X and Y, each in 10 ml in water. Okay, so prepare separately a 5% solution of any. Prepare so X and Y. Take one of the following sets X and Y of chemicals. So X and Y. So copper sulfate, sodium carbonate, barium chloride, sodium sulfate, lead nitrate, sodium chloride. Take one of the following sets X and Y. Take one of the following sets X and Y of chemicals. So X and Y. So X is copper sulfate, Y is sodium carbonate. So X barium chloride, Y sodium sulfate. X lead nitrate, Y sodium chloride. So prepare separately a 5% solution of any one pair of substances listed under X and Y, each in 10 ml in water. Each in 10 ml in water. So take a little amount of solution of Y. Take a little amount of solution Y in a conical flask and some solution of Y in a conical flask and some solution of X in a ignition tube. So hang the ignition tube in the flask carefully. See that the solution do not get mixed. Put a cork on the flask. Okay, so this is the uh, here we take the solution of X, here we take the solution of Y. Small ignition tube. Okay, conical flask is this, and a thread. So this thread, and close it with cork. So now so now ignition tube containing solution of X dipped in a conical flask containing solution of Y. So ignition tube containing solution. Ignition tube containing solution of X. Ignition tube containing solution of X dipped in a conical flask containing solution of Y. Solution of Y. So weigh the flask with its contents carefully. Weigh the flask. Weigh the flask with its contents carefully. Now tilt and swirl the flask so that the solution X and Y get mixed. Weigh again. What happens in the reaction flask? Do you think that a chemical reaction has taken place? Why should you put a cork on the mouth or the flask? does the mass of the flux and its contents change? So law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. So now, after reading this, after reading all this, now they are saying this is the definition of law of conservation of mass. So why can't you say first? Why is this book so damn noisy or irritating? Now they are saying this is the law of conservation. So you should already told in the first place. Law of conservation of mass states that mass can neither be created nor be destroyed in a chemical reaction. We know that law of conservation that said. Like if I give you an example like this, see, H2O, I take H2O of, sorry, 4 gram plus O2. O2 how much? 32 gram I take here, equals to H2O. This is 36 gram. So now who are the now big teachers, big teachers and big teachers and big knowledge gainers will tell that this equation is wrong. This equation is wrong. They cry in corner. Now, so let's fix the equation. So if I add 2 here, if I add 2 here, it is balancing out, right? Sorry, if I make a mistake here, this will be H2. Now it's right. So 34 gram I take hydrogen and 32 gram I take oxygen. And it will always give me the sum of this. Always give me the sum of the reactants equal to sum of the products. Always. That's what is saying. Neither be created nor destroyed. So here is a small theory that Dalton, what it said. John Dalton was born in a poor Weber family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life there, teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. So John Dalton was born in a poor Weaver. John Dalton was born in a poor Weaver's family in 1766 in England. He began his career as a family 766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal in 1793. 7 years later, he became a school principal. 7 years later, he became a school principal in 1793. Dalton left for Manchester. Dalton left for Manchester to Dalton left Dalton left for Manchester to teach mathematics, physics and chemistry in Dalton left the Manchester to teach mathematics, physics and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point of the study of matter. Okay, so he's a good scientist. Now, what it's a law of constant proportion. So anyone who's watching, you can just remember, any students, if you only just remember that atoms more studying, right? So atoms, I have two atoms or moles, or you can say there are two. Anthony L. Lavoisier gave us two important laws. So first one is this law of conservation mass, and second one is law of constant proportion. What it says, so Lavoisier along with other scientists noted that many compounds are composed of two or more elements, and each such compound had the same element in the same proportions, irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1 is to 8. 1 is to 8. For who? In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1 is to 8. Whatever the source of water, thus, if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in nitrogen and hydrogen are always present in the ratio of 14 is to 3 by mass. Whatever the method or source, whatever the method, so hydrogen always, like ammonia, nitrogen and hydrogen are always present in the ratio of 14 is to 3 by mass whenever the method of the source from which it's obtained. So they are saying that you cannot change the water, thus if 9 gram water is decomposed, you cannot change the water ratio. It says that it doesn't matter where the source come from, water source come from, and where you take, where you give, or you always find water in water, the water, the amount of hydrogen, no, the amount of proportionate hydrogen or oxygen always 1 is to 8 remaining in the water. It doesn't matter the where is the source. So similarly saying thus if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio. Says always present in the ratio 14 is to 3 by mass. 14 is to 3 by mass. Whatever the method or source from which it is obtained. So this led to the law of constant proportion. This led to the law of constant proportions, which is also known as law of definite proportions. This law was stated by Proust as in the chemical substance the elements are always present in definite proportions by mass. The next problem, the next problem faced by scientists was the next problem faced by scientists was the next problem he says to scientists was to give appropriate explanation of these laws. Okay, so British chemist John Dalton provided the basic theory about the nature of matter. So Dalton picked up the idea of divisibility. So who picked up the idea of divisibility? Dalton. Divisibility of matter, which was till then just a philosophy. So till then it's just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of theory provided an explanation for the law of according to Dalton's atomic theory. All matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. So the postulates of theory may be stated as follows. So first one, all matter is made of very tiny particles called atoms which participate in chemical reactions. Okay. Second, atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. So according to Dalton's atomic theory, all matter, whether an element or compound or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows. 1. All matter is made of very tiny particles called atoms. Okay. Which participate in chemical reactions. Atoms are indivisible particles. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. So atoms are indivisible particles which cannot be created Atoms are individual particles which cannot be created or destroyed in a chemical reaction. It cannot be created or destroyed in a chemical reaction. So now atoms of a given element are identical in mass and chemical property. Atoms of different elements have different masses and chemical properties. It also said atoms combine in ratio of small whole numbers to form compounds. The relative number of the and kinds of atoms are constant in a given compound. So you will study in the next chapter that all atoms are made up of still small particles. Okay. In a reaction, 5.3 gram of sodium carbonate and reacted with 6 gram of acetic acid. The products were 2.2 gram of carbon dioxide, 0.9 gram water and 8.2 gram of sodium acetate. Show that these observations are in agreement with law of conservation of mass. So sodium carbonate plus acetic acid, sodium acetate plus carbon dioxide plus water. So hydrogen and oxygen combine. These are the fucking, sorry for the use. So hydrogen and oxygen combine in the ratio of 1:8 by mass of to form water. So what mass of oxygen gas would be required to react completely with 3 gram of hydrogen gas? So these are the question you have to find out the answers. So which postulate of Dalton's atomic theory is the result of the law of conservation of mass? So which postulate of Dalton's atomic theory can explain the law of definite proportion? Have you ever observed a mason? Have you ever observed a mason building walls? From these walls a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. How big are atoms? So atoms are very small. They are smaller than anything that we can imagine. What is an atom? So have you ever observed what is an atom? Have you ever observed a mason? I guess it will mention. Have you ever observed mason building walls? From these walls a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. Similarly, the building blocks of all matter are atoms. Okay. How big are atoms? So atoms are very small. They are smaller than anything that we can imagine, imagine or compare with. So more than millions of atoms when stacked would make a layer brick as thick as this sheet of paper. You get that? More than million. So atom has a radius. So we already said that atoms are nearly shaped like a spherical shape. So if it is a spherical shape, then it will has a radius. It will have a radius, right? So that's what it's saying. So atom radius is measured in nanometers. So atom radius is measured in nm, nanometers. So we know that 1 nm equal to 10 to the power minus 9 m, right? Sorry, 1 nanometer, no. Yeah, we can say that. We also can say that this, yeah, you are right, 1 nm equal to 10 to the minus 9, or also we can say that 1 meter equal to 10 to the power 9 nm. We also say this, so now, so now now relative sizes. What is relative sizes? So relative sizes, they are saying that we know that atoms are spherical shape, they have the radius. So radius examples, they are giving some examples of radius. So some examples of radius, like hydrogen also atom, right? So hydrogen atoms radius they are giving in sizes. So they are giving atoms of hydrogen radius is 10 to the power minus 10, molecule of water's radius 10 to the power minus 9, molecule of hemoglobin 10 to the power minus 8, grain of sand 10 to the power minus 4, ant 10 to the power minus 3, apple 10 to the power minus 1. These are the examples. Also see here, what are the modern day symbol of atoms of different elements? So Dalton was the first scientist to use the symbol. So who was the first scientist to uh, find out the symbols or suggest the symbols? Dalton. So Dalton was the first who used the symbols, very specific sense. When he used a symbol for an element, he almost meant a definite quantity of that element, that is one atom of that element. So Berzelius suggested that the symbols of elements be made from one of the two letters of the name of element. So first is hydrogen. How hydrogen? So this is, he suggested hydrogen look like this symbol. Carbon symbol this, oxygen symbol is this, phosphorus symbol is this, sulfur symbol is this, iron silver is this, silver, mercury, lead, platina, copper, gold, symbols from some elements proposed by Dalton. So in the beginning, the names of the names of elements were derived. Names of elements derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. For example, copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from English word meaning yellow. Nowadays, IUPAC. Nowadays, who? Nowadays, here is an important thing. Nowadays, IUPAC, International Union of Pure and Applied Chemistry. IUPAC. It's called IUPAC. IUPAC is an international scientific organization. It's an organization, international scientific, who approves names, which approves names of elements, which approve names and elements and symbols also, and units. So many of the symbols are the first one or two letters of the element's name in the English. The first letter of symbol is always written as capital letter, uppercase, and the second letter always small letter. So like example, calcium, we always calcium capital C and small a, and helium H small e. Examples. So now for examples they are giving, so hydrogen, aluminum Al, not Al. Now cobalt Co and not Co. So symbols of some elements are formed. Symbols of some elements are formed from the first letter. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples are chlorine Cl2, zinc Zn. Other symbols have been taken from the names of elements in Latin, German or Greek. For example, the symbols of iron is Fe from its Latin name. Ferrum. Guys, what I'm coming right now. Wait a minute. I'll come just in 2 minutes. Because I have to go washroom, sorry. I've come, guys, don't worry, I have come. Now let's continue. So what I'm saying here, for example, these are the giving examples, right? So symbols of some elements are formed from the first letter of the name and the letter appearing later in the name. Examples are one chlorine, second one zinc, Zn, etc. Other symbols have been taken from the names of elements. Other symbols have been taken from the names of elements in Latin, German, Greek. For example, a symbol of iron is Fe from its Latin name, ferrum. Sodium is Na. Ferrum, Latin name ferrum. Sodium is sodium Na. from natrium. Potassium is K from kalium. Therefore each element has a name and a unique chemical symbol. You got it? So we will see. Now we'll see what it here says, atomic mass, right? So now they are giving us a table 3.1, symbols of what symbols of some elements. Okay, so symbols of some elements they are given, so you can read it right here, and also you have to remember the symbols. These are the very important. So first is aluminium Al, फिर argon Ar, barium Ba, boron B, bromine Br, calcium Ca, carbon C, chlorine Cl, cobalt Co. Second is copper Cu, fluorine F, gold Au, hydrogen H, iodine I, iron Fe, lead Pb, magnesium Mg, neon Ne. Now others nitrogen and oxygen O, potassium K, silicon Si, silver Ag, sodium Na, sulfur S, uranium U, zinc Zn. So these symbols are important for you right now, 9 class 9 10. But after that you need to remember more symbols. So the above table is given for you refer to whenever you study about elements. Do not bother to memorize all in one go within the. So they are saying do not bother to memorize all in one go, but I will suggest you to memorize it, because if you memorize it, that it will help you to do the faster other in chemical reaction, do it faster and other things. Because remembering the key, if you can remember now, you can easily do the other things from they are using. So these symbols and they will use in chemical reaction, so it will help you if you remember properly. So now assign carbon an atomic mass 1 u means, so this mu we call it a mu, also call it a mu, we also call it a mu. So mu or equal to a m u, atomic mass unit you also can call it, or also you can call it mu. So 1 mu, and oxygen and atomic mass is 1.33 mu. However, it is more convenient to have these numbers as passage of time, repeated usage. You will automatically be able to reproduce this symbol. So atomic mass. Oh, what is atomic mass, bro? What is atomic mass, bro? What is atomic mass? So atomic mass. What is atomic mass? What is atomic mass? So the most remarkable concept of that Dalton's most remarkable concept is atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. So according to whose? Dalton's. Each element has a or had a characteristic atomic mass. So the theory could explain the law of constant proportions so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, because these are atoms very small and very difficult to divide and find out their masses. So relative atomic masses were determined using the laws of chemical combinations and the compounds formed. So relative atomic masses were determined. How they determined? Relative atomic mass determined using the laws of chemical combination and the compounds are formed. So let us take the example of compound carbon monoxide CO. Carbon monoxide denoted as CO, formed by carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form CO, right? In other words, carbon combines with 4 by 3 times its mass of oxygen. Suppose we define the atomic mass unit earlier abbreviated as AMU, right? But according to the latest IUPAC recommendations, it is now written as mu, unified mass, as equal to the mass of one carbon atom. Then we would then we would we we would assign a carbon and atomic mass 1 and oxygen atomic mass of 1.33. However, it is more convenient to have these numbers as whole number or as two whole numbers as possible. While searching for various atomic mass units, scientists initially took 1 by 16 of mass of an atom of naturally occurring oxygen as the unit. So this was considered relevant due to two reasons. These are considered relevant due to two reasons. What are the reasons? So first one is oxygen reacted with large number of elements and formed compounds. And second one is this atomic mass unit gave masses of most of the elements was whole numbers. The first one is oxygen reacted with a large number of elements and formed compounds. And the second one is this atomic mass unit gave masses of most of the elements as whole numbers. As whole numbers. So, however, in 1961, for a universally so sorry. So, however, in 1961, for a universally accepted atomic mass unit, carbon 12 isotope, right? Carbon has 12 isotope. Carbon 12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12, 1 by 12th, the mass of one of atom of carbon 12. The relative atomic masses of all elements have been found with respect to an atom of a carbon 12. So imagine a fruit seller selling a fruits without any standard weight with him. He takes a watermelon and says this has a mass equal to 12 units. So 12 watermelon units or 12 fruits mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling relative to the mass of one piece of the watermelon. Now he sells his fruits by relatively few fruit mass unit FMU as figure 3.1. So A, B, C. So now D. So watermelon 12 pieces 1 by 12 of watermelon. How how the fruit seller can weigh the fruits using pieces of watermelon. So similarly the relative atomic mass of the atom of an element is defined as average mass of an average mass of the atom as compared to 1 by 12th the mass of one carbon 12 atom. So table 3.2. So atomic mass of a few elements. So elements and atomic mass U. So hydrogen 1, carbon 12. Atomic masses and elements. They are giving some few examples. So atomic mass 1, carbon 12, nitrogen 14, oxygen 16, sodium 23, magnesium 24, sulfur 32. chlorine 35.5, calcium 40. So how do atoms exist? So atoms of the most elements are not able to exist independently. Atoms form molecules and ions. These molecules of ions aggregated in large numbers to form the matter that we can see, feel or touch. Questions. Define the atomic mass unit. Why is it not possible to see an atomic with naked eyes? आंधी बनकर. So what is a molecule? So a molecule is a, now we are going for molecule. Atom, we learned atom, now we're going for molecule, right? So what is a molecule? So a molecule is a group of two. So molecule is a general group of two atoms or more atoms that are chemically bonded together. That is, that is tightly held together by attractive force. Says a molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or the different elements can join together to form molecules. So this is called molecules together, that is tightly together by attractive forces. This is molecule. So now molecules of elements. So molecules of elements. So wait guys, wait. I have to drink some water. So I have come here. So now, so let's continue. So we're learning molecules of elements, right? So here it says the molecules of an element are constituted by the same type of atoms. So molecules of many elements such as argon, air, helium, He, etc. are made up only one atom of that element. Okay, so but this is not the case with most of the non-metals. For example, a molecule of oxygen consists of two atoms of oxygen, and hence it is known as diatomic molecular O2. So here they are saying for metals they are using, for metals, those are metals, they are using one type of they are using one molecules like argon, helium, they are only using one molecule made up of only one type of that element. But this is not the case of this is but they are saying this is not the case for non-metals like oxygen use two molecules like O2, diatomic. If three atoms of oxygen unite into a molecule instead of the usual two, we get ozone O3. The number of atoms constituting a molecule is known as its atomicity. So metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number. So atoms bonded together. So let us look at atomicity of some non-metals. Atomicity of some non-metals. So here are some non-metals atomicity, like atomicity of non-metals. So type of non-metal. So first argon. Argon is a non-metal, monatomic, because only use one type of molecule. That's why it's called monatomic. Why it's only take one type of molecules and why it called monatomic? It also, argon is also a noble gas. It also is a noble gas. Remember, helium also monatomic. Those are noble gases. They are monatomic. You can also remember like that. They noble gases are always use one type of one type of atom, or also one type of molecules. Now oxygen is diatomic because using two molecule. Hydrogen diatomic, nitrogen diatomic, chlorine diatomic, phosphorus tetratomic. He uses three type molecules. Sulfur polyatomic, many molecules he use. Now molecules of compounds, right? So atoms of different elements join together in definite proportions to form molecules of compounds. Few examples are given in the table 3.4. So table 3 molecules of some compounds. Okay, so compound water H2O. So here combining elements are hydrogen oxygen, the ratio is 1:8. Ammonia NH3, the combining elements nitrogen hydrogen, for 14:3. Now the carbon dioxide CO2, carbon oxygen 3:8. So now here is the activity referred to table 3.4, ratio by mass of atoms present in molecules, and table 3.2 for atomic masses of elements. So find the ratio by number of atoms of elements in the molecules of that compound of 3:4. The ratio by number of atoms for a watermelon can be found as follows. Element hydrogen oxygen, ratio by mass 1:8, atomic mass 1:16. Why 16? Because oxygen atomic mass is 16 and hydrogen atomic mass is 1. Mass ratio by atomic mass. So was mass ratio by atomic mass. So here hydrogens are same 1 by 1 then 1, and oxygen is 8 by 16, so 1 by 2. So the simplest ratio is 2:1. 2:1. So thus the ratio by number of atoms of water is H:O, 2:1. So what is an ion? So now what is a ion? So ion basically called these signs, like I am writing Cl minus, Cl plus, Cl minus, Cl here writing Cl minus, Na plus. These are the ions. These are called ion. So compounds composed of metal and non-metals contains charged species that changed that their changed spices are known as ions. So ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called an anion, and take the positively charged ion, a cation. So take for example sodium chloride NaCl. Its constituent particles are positively charged. Sodium ions Na plus and negatively charged. So what it called? Let me read again. So this is compounds composed of metals and non-metals contain charge charge species. Okay, species, right? Yeah. So the charged species are known as ions. Okay, ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called, okay, so the negatively charged ion is called anion and positively charged called cation. Take for example sodium chloride, sodium chlorine, sodium chloride NaCl. Its constituent particles are positively charged, like sodium ions Na plus, negatively charged is Cl minus. Here is Cl minus. So a group of atoms carrying a charge is known as polyatomic ion. A group of atoms carrying a charge is known as polyatomic ion. Table 3.6. Table 3.6. See the table 6.3. We shall learn more about the formation of ions in chapter 4. Okay, got it. In chapter 4, where is the atomic structure, we will learn more. What happened to my parcel? Wait a minute, guys. Continuing with packaged. Okay, so package right of final. Okay. Okay. Where is the okay, let's continue, guys. So some ionic compounds in this table. So ionic compounds are and constituting elements and ratio by mass. Okay, so calcium oxide Ca, calcium and oxygen, calcium oxide, sorry, CO, calcium C and oxygen 5:2. Magnesium sulfide, magnesium and sulfur, so 3:4, the ratio by mass. Okay, Sodium chloride, sodium and chloride, 23 is to 35.5 is the ratio. So now writing chemical formula. So writing chemical formula. So the chemical formula of a compound is a symbolic representation or of its composition. So the chemical formula of different compounds can be written easily. For this exercise, we need to we need to learn the symbols and combining capacity of the elements. So the combining power or capacity of an element is known as its valency. Valency, it's a important thing. Valency, we will learn in more other topics. So valency can be used to find out how the atoms of an element will combine with the atom of another element to form a chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. So human beings have two arms. Sorry. So human beings have two arms and an octopus has eight. If one octopus has to catch hold of few people in such a manner that all eight arms will octopus and both arms of all humans are locked. So how many humans do you think the octopus can hold? How many? So represent the octopus with O and humans with H. Can you write a formula for this combination? Do you get OH4 as the formula? The subscript 4 indicates the number of humans held by octopus. The valencies of some common ions given in table 3 is to 6. We will learn more about valency in the next tutorial. Yes. So names and symbol of the ion, how you use the ions. So name of the ion sodium, symbol Na plus, potassium, symbol K plus, silver Ag plus, copper Cu plus, magnesium Mg2 plus, magnesium Mg2 plus, calcium Ca2 plus, zinc Zn2 plus, iron 2 Fe2 plus, copper 2 Cu2 plus. So copper 1 is Cu1 plus and copper 2 is Cu2 plus. So copper is two different ions. So aluminium Al3 plus, iron 3 Fe3 plus. Iron also has different. So now these are the metallics. Now non-metallic element like hydrogen H plus, hydride H minus, chloride Cl minus, bromide Br minus, iodide I minus, oxide O2 minus, sulfide H2 minus, oxide O2 minus, sulfide H2 minus, nitride N3 minus. Now polyatomic ions like ammonium NH4 plus, hydroxide OH minus, nitride NO3 minus, hydrogen carbonate CO3 minus, carbonate CO3 2 minus, sulfite SO3 2 minus, sulfate SO4 2 minus. So phosphate PO4 3 minus. Some elements show more than one valency. A Roman numerical shows their valency in a bracket. So the rules that you have to follow while writing a chemical formula are follows. The valencies or charges on the ion must balance. Okay. When a compound consists of a metal and non-metal, the name of the symbol of the metal is written first. Name of the symbol of the metal is written first. Okay. For example, calcium oxide. So Ca first, calcium CaO, then oxide. Sodium chloride Na first and Cl. Iron sulfide FeS. Copper oxide Co, etc. Where oxygen, chlorine, sulfur are non-metals and are written on the right, whereas calcium, the sodium, iron and copper are metals and are written on the left. Okay. So in compounds formed with polyatomic ions, the number of ions present in the compound is indicated by and closing the formula of ion in a bracket and writing the number of ions outside the bracket. For example, MgOH whole 2. The number of ions present in the compound is indicated by enclosing the formula of ion in a bracket and writing the number of ions outside the bracket. For example, MgOH whole 2. In case the number of polyatomic ion is 1, the bracket is not required. For example, NaOH. Okay. If number is 1, then bracket is not required. If number is more than 1, then bracket is required. Now formulae of simple compounds. So the simplest compounds which are made up of two different elements are called binary compounds. Valencies of some ions are given in table 3.6. You can use these to write formulae for compounds. So while writing the chemical formulae for compounds, we write the constituent elements. And their valency, constituent elements and their valencies as so below. Then we must cross over the valencies of the combining atoms. Okay. Examples. So examples: formula of hydrogen chloride, symbol. Examples: formula of hydrogen chloride, HCl, symbol H. H valency was 1. Cl valency 1. How? Cl is 17, right? Yes. So Cl is 17. So 2 8 8 2 8 10 6 6. Cl is 17. Yes, Cl is 17. If 17, then Cl need 1. So Cl need 1 electron to get octant. So you will not understand what I'm saying octant. You will understand it next chapter. So just bear with me. So here's, that's why we use 1 here, valency, and H valency 1 was. Now we are doing cross. Formula of the compound would be HCl. Cross multiplication you can say it, or cross multiplication, not cross giving. Like Cl1 will go to H and Cl1 H1 go to Cl. So formula 2, formula of hydrogen sulfide. So symbol HS, right? So valency H is H and sulfur is 2. So now 2 is going to H. Here you can understand 2 is going to H and 1 is going to sulfur. That's why you write H2S. Now formula 3, formula of carbon tetrachloride. Formula of carbon tetrachloride. Tetrachloride here says tetrachloride means 3. Tetrachloride. Carbon tetrachloride. Tetrachloride means 3 or 4. Carbon tetrachloride we write like this, CCl4. So here is C and here is Cl. Cl we know 1 and C is 4. So it's go this, it's go this. So that's why we write CCl4. So for magnesium chloride, we write the symbol of cation Mg2 plus first, followed by the symbol of anion Cl minus. Then their charges are crisscrossed to get the formula. So formula like Mg and Cl, 2 plus and 1 minus. So why not this? Why not we use here? For magnesium chloride, we write the symbol of cation Mg2 plus first, followed by the symbol of anion Cl minus. Then their charges are crisscrossed, and charges are crisscrossed like MgCl2. For metals we use this, right? I guess for metals we use ions. So thus in magnesium chloride there are 2 chloride ions Cl minus. For example, for each magnesium ion Mg2 plus, the positive and negative charges must be balance each other, and the overall structure must be neutral. So note that in the formula the charges on the ions are called not indicated. Some more examples are: A, formula for aluminium oxide. Formula for aluminum oxide, symbol AlO. Charge 3 plus 2 minus. So formula Al2O3. So B. Formula for calcium oxide. Formula for calcium oxide what? Symbol CaO. Charge 2 plus 2 minus. Formula for aluminum Al3 plus we know, and oxide O 2 minus, because need octant. So you will understand more clearly in the next chapter, because of when you learn about valency, then you can understand more properly. Symbol CaO 2 plus 2 minus. So here the valencies of two elements are the same. You may arrive at the formula Ca2O2, but we simplify the formula as CaO. Okay, so now formula of sodium nitrate. So formula of sodium nitrate, what it says? Formula of sodium nitrate. So symbol divided formula. So NaNO3, charge 1 plus 1 minus. So formula NaNO3. That's simple. Formula of calcium hydroxide, symbol slash formula. So calcium hydroxide CaOH, charge 2 plus and OH 1 minus. CaOH whole 2. Here is something different. Sodium nitrate, symbol slash formula NaNO3. So now note that the formula of calcium hydroxide is CaOH whole 2 and not CaOH whole 2, CHOH2. We used brackets when we have two or more of the same ions in the formula. Here the bracket around OH with a subscript 2 indicates that there are two hydroxyl OH groups joined to the one calcium atom. In other words, there are two atoms each of oxygen and hydrogen in calcium hydroxide. So formula of sodium carbonate. So symbol formula. So NaCO3. So NaCO3, right? So Na is plus 1, CO3 is 2 minus. Formula Na2CO3. Na2CO3. Because there is one. Now in the above example, brackets are not needed if there is only one ion present. Yeah, I know. The formula for ammonium sulfate, formula NH4SO4. So 1 plus NH4SO4, right? So 1 plus 2 minus, no, NH4 whole 2 and SO4. So now they are giving some, write down the formula of this sodium oxide, NaOH, sodium oxide, aluminum chloride, sodium sulfide, magnesium hydroxide, Mg2, Mgc, magnesium hydroxide, MgOH. And write down the names of compound represented by the following formula name: Al2SO4O3, aluminum, aluminum, aluminum sulfuric, right? Aluminum sulfuric, it will say aluminum sulfuric. Yeah. Aluminum SO4, where is SO4? Yeah. Aluminum sulfate, CaCl2, that I calcium, what it did, calcium tetrachloride, calcium tetrachloride, yes, CaCl2, CaCl4, calcium dichloride, K2SO4, potassium sulfate, KNO3, potassium nitride, CaCO3, calcium carbonate. What is the meant by the term chemical formula? What is meant by the term chemical formula? How many atoms are present in a H2S molecule and PO3 minus ion? Atoms are present in H2S molecule. Uh, how many atoms are present in H2S? H2S molecule present is molecule. How many atoms are present? H2, 1, atomic mass, sulfur is 2. So PO4 3 minus ion. PO4 is, let's leave it. Let's go to the molecular mass. So molecular mass, what is molecular mass? If I want to know what is a molecular mass, so molecular mass, in section 322 we discussed the concept of atomic mass. This concept can be extended to calculate molecular masses. The molecular mass of a substance is the sum of the atomic masses of all atoms in a molecule of the substance. So it is therefore the relative mass of a molecule expressed in atomic mass units. So example, calculate the relative molecular mass of water H2O. Calculate the molecular mass of HNO3. So atomic mass of hydrogen is 1U and oxygen is 16U, right? So molecular mass of water, which contains two atoms of hydrogen and one atoms of oxygen. So 2 is 2 into 1 plus molecular mass is simple. You have to know just the masses of atomic masses of the the molecules. Then you will give the answers. This is simple. So that's why 2 into 1 and 1 into 16 is 18 and 63, because you have to know the molecular masses for do that. Formula unit mass, the formula unit mass of a substance is the sum of atomic masses of all atoms in a formula unit of a compound. So formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride, as discussed above, has a formula unit NaCl. Its formula unit masses can be calculated as 1 into 23, 1 into 35.5, because Na for sodium the mass is 23 and for Cl 35.5, so equal to 58.5. Constituent particles are ion. Okay. Calculate the formula unit mass of CaCl2. So atomic mass of Ca plus 2 into atomic mass of Cl. Atomic mass of Ca plus 2 into atomic mass of Cl. So 40 plus 2 into 35.5 into 40. So 111 U. So what have we learned? So what we have learned here? So first, during a chemical reaction, the sum of masses of the reactants and products remain unchanged. This is known as law of conservation mass. Okay. In a pure chemical compound, elements are always present in a definite proportion by mass. Okay. This is known as law of definite proportion. Third, an atom is the smallest particle of the element that cannot usually exist independently and retain all its chemical properties. Fourth, a molecule is the smallest particle of an element or a compound capable of independent existence under ordinary conditions. A molecule is the smallest particle of an element or a compound capable of independent existence. Capable of independent existence under ordinary conditions. It shows all properties of the substances. Now, a chemical formula of a compound shows its constituent, elements, and the number of atoms of each combining element. So now clusters of atoms that act as an ion are called polyatomic ions. They carry a fixed of charge on them. Now the chemical formula of a molecular compound is determined by the valency of each element. Okay. In ionic compounds, the charge on each ion is used to determine the chemical formula of the compound. So there are some exercises we will do in exercises we will do in the next stream. So today the chapter is finished, so only exercises are remaining. So in the next stream we will do the exercises. Also we will start the chapter number 4. So so stream is over now, right? So now we're taking leave. So good afternoon guys, and